In this section, we're going to extend what we did last time to look now not just at series like this, k equals 0 to n, where we would have something like, last time it would look like something like a sub k times x minus a to the k, where it would end at n. This would be a Taylor polynomial centered at a, and we worked with these in last time. So now what we're going to do is free this from needing an n up there and work with things like these where it can go off to infinity. This is an example. These are what a power series looks like. And we're ready to go right into them, believe it or not. The first one that we'll discuss is related to the extremely important geometric series. And remember, this series was good when r was between -1 and 1. We can't plug in 1 because it wouldn't go in here. And it doesn't matter if you plug it in anyways. If you add 1 to itself an infinite number of times, it's infinite. -1 didn't work either because you had an alternating sequence of partial sums. That wouldn't work either. But anything in between was fine. So, since we're used to this and it works between -1 and 1, we could, instead of an r, put a variable x in there and get the series that looks like this. But in order for this series to be defined, we would insist, of course, that x be between -1 and 1. Or a lot of times your book will use this notation instead of that. So there's a lot of stuff that you can do to that you'll be surprised. Let me show you one thing. This may seem sort of weak to have a function whose domain is -1 to 1, but we can actually use this kind of a series to get functions with larger domains. Here's what I mean. Try this as an example. Consider this series. 1 over 1 plus x over 3. Well, according to this formula that I have, I can rewrite this as 1 minus -x over 3. And so that would equal the sum k equals 0 to infinity, -x over 3 to the k. And in this way we get an alternating series that looks like this. So I'll have -1 to the k, x to the k over 3 to the k. But the cool part is right here. Whereas this piece has to be between -1 and 1, our new piece, see what we have then is -1 is less than x over 3 is less than 1. Well, multiply through by 3 and you see that the domain of this particular power series is bigger than -1 to 1. It's -3 to 3. Of course, I can also put a 2x, say something like that here, and decrease the domain. But there's all sorts of things that you can do with this. No problems with a plus or anything like that. You could have, say, something like 5 over 2x plus 3. And then I can still use this series because I could rewrite it like this. 5 thirds times 1 over. Now, if I factor a 3 out of the denominator, I'll get 2/3 x plus 1. And this is the part I'm going to concentrate on for my series. I'll do one more step to make it clear what I'm up to. As before, a plus can be thought of as a double negative, and now it's of the format 1 minus r. And I can plug that in. And of course, to make it look like a regular old power series, this 5/3, assuming the series converges, I could have the 5/3 on the outside or on the inside. It really doesn't matter. and I could rewrite this as k equals 0 to infinity. So down here I'd have 3 to the k, so the denominator could look like 3 to the k plus 1. And then I have an x to the k, I could put that over here. I have a 2 to the k that I could put up here. Then this negative 1 to the k could go here. I didn't account for the 5 yet though, so I could keep the 5 on the outside or have the 5 in here. I think I might keep the 5 out there because it had nothing really to work with in there. So look how complicated of a power series we have, all from this simple formula. Even something like this could be realized into a power series if I rewrite it as 1 over. Now, I'm thinking of completing the square here. So let me make a huge vinculum here and put over there 4x plus x squared. Now, if I had a 4 here, that would make this, what's left here, a perfect square trinomial. So I can make that happen, though. I can add 4 into here so long as I also subtract 4. And so you can see right here, this is going to be 2 plus x, that quantity squared. And then, to make it of the form 1 over 1 minus something, that's what I have to work with, I'm going to factor out a negative 1/3. And when I take the negative 3 from this piece, I'll get a 1, but then I'll get minus 2 plus x squared over 3. Now this whole thing's not in the square, so I could throw that into the power series and get the following. So in this case, the 2 plus x over 3, 2 plus x squared over 3 is like my r in the formula. And now this here, if I wanted to expand it out some, I could rewrite it as negative 1/3 summation k equals 0 to infinity. Then on the top I could have 2 plus x to the 2k. And in the denominator I could have 3 to the k. And of course, what values of x, or what would be the domain of this particular function? Then we would have to put 2 plus x squared between 1 and negative 1. Over 3, of course. Now, when I start solving for something like this, I'll have to multiply through by 3, and I'll get negative 3 is less than 2 plus x squared is less than 1. I'm sorry, is less than 3. But that's not a big deal either. Here, I happen to know that anything to the second power can't be negative. So this negative 3 is not going to happen anyways. So I'm going to adjust my interval as necessary. Now I can go ahead and take the square root of everything, since I'm not dealing with negatives. The square root will, of course, eliminate the square, assuming certain things about x and stuff like that. So let's go ahead and take the square root of everything. The square root operates on non-negative numbers. And it's an increasing function, so it does not change the nature of these, or the orientation of these inequalities. This piece in the middle is actually the absolute value of x plus 2. Well, this I already knew anyways. However, when I say x plus 2 in absolute value is less than 3, I actually mean that negative 3, it's always greater than or equal to 0, so that really doesn't do anything for me. And then when I subtract 2, so our function here is true for x between -5 to 1. If you will, this thing here, which was equal to all that, let me go ahead and put it back. Now, the domain of this function is going to be all real numbers except where the denominator is 0. However, if I'm to say it equals this, I can only operate for those values of x for which the series converges. And so as far as I'm concerned, the domain of this kind of an equation, if you want to call it that, or the domain of a function defined this way, is -5 to 1. Now, one of the things we talked about earlier with power series is what happens at the endpoints. And all the theory as far as the interval of convergence, or at least the radius of convergence, is okay, except it's always necessary to check endpoints. Like for x equals -5, does this actually converge? When x equals 1, does this converge? Well, let's find out. When x equals -5. Now, when x equals -5, let me plug it in here just to make sure that it doesn't zero out the denominator. If I plug -5 into this denominator, I'll get 25 minus 20 plus 1. That's not a 0 in the denominator. So -5 is okay there. Let me plug it into this. I don't even care where it starts and ends, honestly. All I care about is replacing x with -5 and seeing what happens. So I have 2 minus 5 squared, or to the 2k, all over 3 to the k. And here I'll get a -3 to the 2k all over 3 to the k. Oh, I have made a mistake. Right there, I forgot that I took the square root of everything, didn't I? Yes, I sure did. Okay, and then I'll be able to break this up. As before, the 0 is irrelevant here because the absolute value is greater than 0 anyways. I will have x plus 2 will be less than radical 3, be greater than negative radical 3. And now I'll go ahead and subtract 2. All of what I said is still good. If I plug in any values of x in this range, then I'll get a convergent sequence, a convergent series. However, I want to go back and change my interval here. I'll have -2 minus radical 3 is less than x is less than -2 plus radical 3. Now my endpoints are different, of course. So instead, let me start at the left endpoint, -2 minus radical 3, and I'll replace x with that quantity. I don't really care about these. I know I said that, but I wrote it anyways. So I have 2 plus x to the 2k over 3 to the k. That's going to equal summation k equals 0 to infinity. X is being replaced by -2 minus radical 3, so I'll have 2 minus radical 3 to the 2k all over 3 to the k. And this will give me negative radical 3 to the 2k. I'm going to drop the beginning and end of that thing if that's not important for what I'm going to do here. The 2's cancel, and I'll be left with negative radical 3 to the 2k all over 3 to the k. Now, I can do the 2 portion of the power, and I'll get the summation. Negative radical 3 squared is 3 to the k over 3 to the k. And this is an infinite series of 1s. That always adds up to infinity. So I cannot include the left endpoint. If I try the other endpoint, -2 plus radical 3, if I plug it in here, plus here, you'll see a plus here, this will still end the same. And I'll still be ending with this. So I cannot plug in either of the endpoints. So let me give you some information what we have then. This interval, if you will, is called the interval of convergence. And the radius of convergence is radical 3. Let me explain that for a minute. Hopefully you can see the series itself. When you see a 2 plus x peering out at you, you'll know that -2 is the center of the interval. So a picture will go a long way to describe this. So we were centered at -2, and we were allowed to stray to the right by radical 3 and to the left by radical 3. So this interval here, depending on where you came from, these will have little open holes at the end of them, so you indicate that the endpoints are not included. But where does the radical 3 come in? Well, r is the distance from the center to an endpoint. The r, you'll have to forgive the r seeming like a radius, might seem strange, but it stems from a higher level application of this in which the intervals actually might not be an interval in this sense, but it might actually be a circle with a certain radius attached to it. That's more common in higher level math than what we are dealing with here. So higher level terms have come or trickled down to our course. So we're going to focus on this activity for a little bit. Determine the interval and radius of convergence for this particular summation. And notice I didn't, it's whatever it starts at is totally irrelevant anyways. So one of the things that you would do to determine if the series was convergent at all, wouldn't you do the ratio test? Or you might use the root test, but since this isn't something raised to the k power, I'm not going to bother with the root test. It'll be easy enough to work with this. So what we do is we have the limit as k goes to infinity. Now take this to the k plus 1, so we have 2x to the k plus 1 all over k plus 1 factorial, and all that has to be divided by the kth term, which was 2x to the k divided by k factorial. Now, it's easier, believe it or not, it is easier to make these operations happen in context of absolute value, believe it or not, than trying to deal with intervals at the end. Now, what happened? Whenever we would have the k plus 1th divided by k and take the limit, we had to have the result less than 1 in order for it to be considered convergent. So I want to know the x values for which the series has this particular property. Then I'll know that whatever x value it was, that series will converge. So let me continue. I'll show you why the absolute value is really not something to be worried about anyways. Let me go ahead and rewrite this to allow for a lot of canceling, as we did when we were dealing with regular infinite series. What's going to happen in the end, I'll probably get an inequality with x involved that I'll have to solve for. Now, as before, we can do a lot of canceling, like 2x to the k, I can get rid of that. So I just have a 2x here. And the k factorial and the k plus 1 will cancel, and I'll have the limit as k goes to infinity. I'll have my 2x in the numerator, and in the denominator I'll have k plus 1. All of that will be an absolute value. Now the beauty here is that the only thing that I really need an absolute value around is x. Everything else is a positive number. So this is the limit as k goes to infinity of 2 over k plus 1 times the absolute value of x. Here's another great thing. It just so happens that no matter what x happens to be, x is going to be a finite number, so no matter what this happens to be, this limit's going to be 0 because of that denominator. Fix your x. Pick any number that you want for x. Call it 10, 20, whatever. Doesn't matter. After you've placed your x in there, this does not have an x in it, so the limit is not involving x. Whatever number that was. So imagine if you had 2 million over k plus 1. It's still going to go to 0 because k is going to infinity. So here's what we have. 0 is less than 1. This is true for every value of x. What does that mean? Thus, the series, the power series, and once again, I don't care where it starts or where it ends, 2x to the k over k factorial converges on negative infinity to infinity. Right there is the interval of convergence. No matter what x value I put in here, this series will converge. And when it happens, we also call the radius of convergence infinity. So there's my interval of convergence, and there's my radius of convergence. Determine the interval and radius of convergence for So I'll play the same game as I did before. Look at the limit as k goes to infinity. I'm not going to use the root test because this k is not raised to the k power. So this other test is great anyways. I will have 2 to the k plus 1 times x minus 3 to the k plus 1 all over k plus 1 divided by 2 to the k times x minus 3 to the k all over k. And remember, this has to end up being less than 1. So this will equal the limit as k goes to infinity. Let me fix some things up. I'll have 2 to the k plus 1 times x minus 3 to the k plus 1 divided by k plus 1 times k over 2 to the k times x minus 3 to the k. All right, I can take out 2 to the k. I can take out x minus 3 to the k. And then I'll have left the k and k plus 1. So I'll have the limit. K goes to infinity. I'm going to take the k over k plus 1 out here. and then I'll leave the absolute value, and there's a 2 here, I didn't see that still. Put the 2 out there, that's not a big deal. And so what I'll do then is that will leave me with just x minus 3 in the absolute value. Well, the limit of this, using L'Hopital or whatever thing you want to use, is going to be 2. That, of course, that limit does not affect x minus 3. So, in fact, just to show you that in no uncertain terms, in all of these, since the limit involves k, you can factor the x part out. So I have the absolute value of x minus 3. This limit is 2 times 2 is less than 1. Now, I want to get x minus 3 alone, so I'll get x minus 3 is less than 1/2. At this point, you can tell what the radius is going to be. The radius is this number left here. The center is 3. I'm allowed to stray by 1/2 to either side of 3. So I can already tell you that the capital R is going to equal 1/2. That's the radius of convergence right there. Now for the interval, in order to figure that out, I'm going to break this out of its absolute value. The first thing I'll get is negative 1/2 is less than x minus 3 is less than 1/2. And then I'll add 3 to everything. So 3 minus 1/2 will be 5/2. And that'll be less than x, less than, when I add 3 to that side, I'll get 7/2. So, and you can see, if x is centered at 3, 3 is like 6/2. If I go 1/2 to the right of it, I'll get to 7/2. If I go 1/2 to the left of it, I'll get 5/2. As before, we need to still test endpoints. So I need to check x equals 5/2 and x equals 7/2 and see if that results in a convergent series or not. So start with x equals 5/2. Our series was 2 to the k, x minus 3 to the k over k. And now we'll replace x with 5/2. So I'll get 2 to the k, 5/2 minus 3 to the k, all over k. And that will equal 5/2 minus 3 is negative 1/2. So I'll have 2 to the k times negative 1/2 to the k all over k. Well, since they have the same exponent, I can multiply those together, and I end up with some negative 1 to the k over k. Well, this is an alternating harmonic series, and we already know that it converges because these terms are going to 0, decreasing to 0. So we already know the alternating harmonic series converges. So x equals 5/2 is part of our answer. Now let's try x equals 7/2. And so my series 2 to the k, I'll have 7/2 minus 3 to the k all over k. I'll have the same deal as before. 7/2 minus 3, that'll be positive 1/2. When I take positive 1/2 times the 2, I will end up with 1 over k. Now this diverges. I already got the radius is not a big deal. It's still going to be 1/2. But the interval of convergence, I'll call it the I of C, the interval of convergence, is 5/2, 7/2. And the radius of convergence is 1/2. Same deal. Find the radius and interval of convergence. Except now, since everything is to powers, it still wouldn't be hard to do everything like before and just use the ratio test. But just as an alternative, I'm going to use the root test. The root test is a lot easier than people give it credit for. It looks like this. The limit as k goes to infinity. I want the kth root of, now I've got to work with the absolute value of the series. And remember, the same deal worked with the root test. We needed it to be less than 1 also. Well, here all the k's go away, and the absolute value is going to wipe out the -1. So this left side just becomes x cubed. You've got to keep the absolute value around x, because I don't know if it's positive, negative, or whatever. But then in the bottom, I got 27. And that's less than 1. You see how, I mean, basically what this has done is a lot of simplifying for you. I'm going to multiply through by 27. And now I'm going to take the cubed root of both sides. As long as you're dealing with non-negative numbers, the cubed root is an increasing function. So I'm going to take the cubed root of x cubed, and that'll be less than the cubed root of 27. Well, then over here I'll get the absolute value of x will be less than 3. And so then we have -3 is less than x is less than 3. So there is our interval of convergence. I don't care if you give to me an interval form or in this format. Actually, I'm not done. I shouldn't have done that. Let me Control-Z that. Control-Z what I just wrote, because I didn't mean to do that. I have to check the endpoints before I describe the interval of convergence. But now, can you tell that the radius doesn't care about endpoints. The radius will be 3. Remember, the radius is from the center to an endpoint. So I've got that locked in. So now check the endpoints. And I'll start with x equals -3. So that will give me, remember the series I was working with was -1 to the k, x to the 3k, divided by 27 to the k. Now replace x with -3. I'll tell you what, to keep everything in terms of k, I'm going to take -3 and take it to the 3rd power. That'll still keep it negative. -1 to the k times -27 to the k all over 27 to the k. Well, the nice thing about these two things is the negatives will cancel when I multiply them together. So what will happen then is I will get 27 to the k over 27 to the k, and that will be an infinite sum of 1s, which is infinity. So it does not work for that endpoint. Now we'll try x equals 3. Will it work for that one? So now I'm going to work with -1 to the k. Then I'll have 3 to the 3k all over 27 to the k. And I'll do the same thing I did before. I'll have the 27 to the k's will cancel actually, and I'll be left with this. We know this diverges because the sequence of partial sums oscillates, I think, well, it depends on if it starts at negative or positive, but it oscillates it's either 0 and -1 or 0 and 1. It really doesn't matter. Since it oscillates, it doesn't have a limit. So what I said before, the interval of convergence, while it was too premature, is -3 to 3. Or, if you prefer, you can write it as -3, 3. Now, something extremely powerful I'm about to show you. I think we're on example 7. We already know that 1 minus the absolute value of 1 minus x, not the absolute value of it, this is defined for x between -1 and 1. That means if x is between any of these numbers, when you plug it in, you will get a convergence series. But check this out. What if what about this? What about integration? And besides integration, differentiation. This is where we are going to take off into hyperspace. This is when the power of these power series will become evident. It just so happens, I'll take a moment here to describe this to you. The world of science and everything else actually works with this. It turns out that most integrations can't be done by hand, and so they have to be estimated numerically, and it almost always involves power series. In fact, everything involves a power series if you intend to get more and more and more accuracy. The more accuracy you need, the more terms you have to calculate. So the fact that we have a theory that will allow us to go all the way to infinity allows for everybody to operate with these functions in complete comfort, knowing that whatever they'll put in there, as long as it's in the parameters we set forth, will give us a convergent sequence or a convergent series, and therefore it's an answer that can be found. This series will actually be doable so long as we realize that the x values that we're working with are between -1 and 1. So I'm going to take this out of here, and you might find it useful to write this series out because it might help you integrate it. So this series was 1 plus x squared plus x cubed, and that went on forever. And then you can integrate each of these, what they call term by term. So when I get this, I'll get an x, then I'll get an x squared over 2, and then I'll get an x cubed over 3, and then I'll get an x to the 4th over 4, and that will go on and on. Somewhere put a plus c. However, this side, if you let u equal 1 minus x, then du is -1. And of course then that will be negative ln absolute value of u, but I'll put my 1 minus x back. And now if you want to determine the value of c, let x equal 0. X equals 0 is right smack dab in the middle of -1 to 1, so I can plug it in. So I'll have negative ln of 1 will equal, the zeros for x will make this entire thing disappear except for just the c. So I'll put big fat 0 plus c, but the natural log of 1 is 0, so c is equal to 0. So what I have then is I have ln absolute 1 minus x equals, and what I'll do is instead of have this, well, let me write it and then I'll write it again. It's probably the best to then put it back into summation notation after you've got a feel for this. So for particular, it looks like I'm going to have an x to the k, but then I have over k. So I'll do x to the k over k. And now I would want to start k at 1. This way, when k is equal to 1, I'll have x to the 1 over 1. That'll take care of that part. When k is 2, I'll have x squared over 2, etc. Now, I can go one step further. I can multiply both sides by a negative. And we know that this is true. However, each series that we deal with, while the radius will be the same, the radius is still 1 as it was before, we could pick up endpoints. It's not going to grow any bigger than that, though. So let's check out the endpoints. So we'll start with x equals negative 1. And I'm looking at this series right here. I don't care about the negative aspect of it, but when I look at x to the k over k, and once again I'm dropping the things because for this particular thing it doesn't matter where it starts at. So that will give me negative 1 to the k over k. Once again, this is a harmonic, this is an alternating harmonic series, so it most definitely converges when x equals negative 1. It's the alternating. So, x equals negative 1, it works. How about x equal 1? Well, when I plug in x equal 1 into that series, this time it's not going to work because this is the harmonic series, and that equals infinity. And it wouldn't have been good anyways. Trying to plug in x equal to 1 into that formula wouldn't have been good. So what I have then is the natural log of 1 minus x in absolute value equals summation x to the k over k, but I need x to be between negative 1 and 1, but it can include negative 1, but not include 1. Now, since it works for negative 1, I'm going to plug x equal negative 1 into the previous answer. So I'll plug it into both sides. This time I will care where it starts and where it ends. So let's go back to where did I start this thing? Right here. Well, on the left, I'll get 2 inside the absolute value, so I'll get the natural logarithm of 2. And on the right, I'll have my negative in the front, but then this will be negative 1 over 1, so I'll have negative 1 plus 1/2 minus 1/3 plus 1/4 minus dot dot dot. And now then I'll multiply through by the negative, and I will get 1 minus 1/2 plus 1/3 minus 1/4, and that goes on forever. But then you have a very cool looking expression for the natural logarithm of 2. When we encountered this before, I told you that 0.693 was a number that a mathematician would recognize. Well, the natural log of 2 is 0.693 to 3 decimal places. Alright, so I would like to find a power series representation for the arctangent of x. And before I do one, what I'm going to do is take the derivative of arctangent of x. And we know this to be equal to 1 over 1 plus x squared. Well, we do have a series for that. If you rewrite this as 1 minus negative x squared, I can now use the geometric series for it. And once again, this is where so many things are dependent on that particular series, it's not even funny. This will equal the sum from k equals 0 to infinity, and then I'll throw the negative x squared to the k. But we have to have that the absolute value of negative x squared is less than 1, with endpoints still needing to be determined quite yet. And, well, the absolute value of negative x squared is the same as x squared anyways. Well, if x squared is to be less than 1, then there's no question that x has to be between negative 1 and 1. I think what I'll do is rewrite this as negative 1 to the k times x to the 2k. And remember, this was equal to originally d over dx arctangent of x. So what do I want to do? I want to integrate both sides with respect to x. So remember, when you take an integral, and you integrate something that was just differentiated, they'll cancel each other out. But over here, I will have now once again, I wouldn't, some books will have you bring the integral inside of here and then integrate term by term while keeping a series. I think that's too complicated, especially when you're new to series and things like that. What I recommend you doing is the right-hand side. Write out the first several terms so you know how to integrate term by term. So I'll leave my integral sign there, and then I'm going to write some of these out. Like when k equals 0, negative 1 to the 0 is still 1, so I'll get x to the 0, so that'll be a 1. And then when k equals 1, I'll get minus x squared, then I'll get plus x to the 4th, minus x to the 6th, and that goes on. This will allow you then to integrate, I think, easier than trying to keep it in series notation or summation notation. So I'll get an x minus x to the 3rd over 3 plus x to the 5 or x to the 5th over 5 minus x to the 7th over 7, and this goes on. So you can see it's just the odd terms that are involved here. And then we'll put a plus c. Of course, the dx is canceled out, and I'll have, will equal that. Of course, you can plug in x equals 0. Arctangent of 0 will then equal 0 minus 0 to the 3rd over 3 plus 0 to the 5th over 5 minus 0 to the 7th over 7. And that goes on and on and on, plus c. Well, these all zero out. Arctangent of 0 is 0. 0 will equal 0 plus c, which means that c equals 0. So arctangent of x equals x minus x to the 3rd over 3 plus x to the 5th over 5 minus x to the 7th over 7, and that goes on and on and on. And this is good for negative 1 less than x less than 1. I said that a while ago. but we still have to check the endpoints. So this will be endpoints. Let me pull the series back up, but I think what I'm going to do, I'll find it interesting, or find it easier, I mean, if I put it into a series form. So we're starting at x, a positive x, so I can do something like k equals 1. If I start at k equals 1, then I can do like an x to the k, but then at this k looks like it's over k, and it's only odd powers. So what I can do, let me change this to 2k minus 1. That way when k is 1, I'll have x to the 1. When k is 2, I'll have x cubed. When k is 3, I'll have x to the 5th. And the denominator can be exactly the same thing, like so. And then in order to get it to alternate, I can do negative 1 to the k plus 1. Now that I think about it, I think I might be able to do this in a little easier fashion. That certainly will work, but I think this might make life a little bit easier if I do it this way instead. Let's take out the let's take out the plus 1 and change these 2k minus 1s to 2k plus 1s. Now it works just as well. The only thing I like about it is it's a little bit cleaned up, I think. So if k is 0, negative 1 to the 0 is going to give me a positive. When k is 0, 2k plus 1 will give me a 1. And then when k is 1, 2k plus 1 will give me 3. So yeah, I kind of like this version a little bit better. Now let's go ahead and plug in this point. So I have tan inverse of negative 1 will equal negative 1 to the k, and then I'll put a negative 1 in for x now. Negative 1 to the 2k plus 1, and then I will also have a 2k plus 1 down below. And when I put these together, I am going to have, I'm dropping this now because it's really not that big of a deal to have it starting at k equals 0. I'm just doing some work with the series. I think what I'm going to do is put these things together. This, if you look at 2k minus 1, this is always going to be negative because 2k plus 1 is an odd number. A negative to an odd is always negative. And then this one right here will be 1, then negative 1, then 1, then negative 1. So if I have something that alternates times something that is always negative, I can actually change it to this. Negative 1 to the k times negative 1. It's going to be the same thing because it's always odd. This is always negative over 2k plus 1. And then when I put these together, I'll have negative 1 to the k plus 1 over 2k plus 1. And it really doesn't matter. This here is going to alternate between positive and negative. This piece will decrease to 0. So this is decreasing to 0. That's the terms 1 over 2k plus 1. But then the negative alternates. So that tells us by the alternating series test, we'll be able to have, this will have a sum. Well, let me go ahead and put back in the beginning and ends of where I did all this stuff before. Let's see, we started at k equals 0, k equals 0. So I'm going to put k equals 0. to infinity. And then on the other hand, I'll leave this to the reader to see if you can get it to do this. Tan inverse of 1. If I plug in, I'll just do it. I don't think it's that big of a deal. If I plug in x equal to 1, then this negative 1 to the k will still alternate. And with it alternating like this fits the same pattern as the other one, so it's also going to converge. And I think you'll find this rather cool, what's going to happen next. If the arctangent of 1 is equal to pi over 4. And over here, I'm going to write it out just so you can see it. When k is 0, I will have 1 over 1. I'll have just 1. But then when k is 1, I will have negative 1 over 2. Over 3, sorry. And here's what's going to happen. Pi over 4 can be written as an infinite series. More importantly, the arctangent of x is equal to the series k equals 0 to infinity, negative 1. I'll fix what I had before. Let me come back to arctangent. Here it is right here. If we started at k equals 0, I'll have this as my formula for arctangent. So let me get that out of there. Then I'll have x to the 2k plus 1 over 2k plus 1. But then x is allowed to be negative 1 and 1. So there's an infinite series for it. Notice, because I made use of the series that I had for the geometric series was used. Let's go back. Right here, when I took the derivative of arctangent, here I have a geometric series. And because I was able to manipulate the geometric series through integration or division, I was able to arrive at a final result instead of doing it all by hand, where I take the derivatives and plug in 0 and then create the series myself. All right, compute the interval of convergence and radius of convergence for the following series. The first thing you would either do is the ratio test or the root test to determine what values of x this will be good for. So I'll start with I'll do the root test. Why? Because it's raised to the 2k power. So this right here needs to end up being less than 1. So let's see what happens. The k's will cancel, and look what I'll have. I'll have x squared plus 1 squared less than 1. Well, no matter what you plug in for x squared is not going to be negative. So no matter what, whatever's in here is greater than 1. X squared plus 1 is, well, it's greater than or equal to 1 no matter what. Because even when x is 0, you'll get 1. So there's no way this can be less than 1. There's no solution. So I guess you would say that the interval, if you want to give it an answer, of convergence would be the empty set. And the radius of convergence, you wouldn't say 0, it just is non-existent. You know, there are some series that will work only for like x equals 0, so it has a 0 radius of convergence, and that's what you go with. But here, I can't even begin this one, so there's no way, shape, or form this is converging for any values of x. Always, so maybe I'll just say always divergent. And you could have done that a lot faster too than going through, well, that's not much to do. Like I said, the root test is quite a bit often easier than it seems like it should be. It seems really complicated, but notice I didn't need the absolute values here because everything was positive. I took the limit away because, well, all the k's were gone. So the things left were not bound by any limits. Let's try another example. Let's call this example 11. And here we want to compute the interval of convergence. Oh, I was going to put I of C, but I guess I forgot. So compute the interval of convergence and radius of convergence for, what do we have here? We have the sum k equals 1 to infinity x minus 2 to the k all over 3 to the 2k. And you might even think it's simpler if you rewrite this. I don't care where it starts, to be honest, because these don't care where it starts. So I'm going to drop that. I have x minus 2 over 9 to the k power. If I do the 3 squared first, I'll get a 9. But everything will be to the k. To me, this is kind of a series that is begging us to use the root test. So, and they call that rho. That's going to equal the limit as k goes to infinity, the kth root of the absolute value of x minus 2 over 9 to the k. And that's supposed to end up being less than 1. Here the same situation occurs. The k's absolutely wipe each other out, and we're left with x minus 2 over 9 is less than 1. I don't need those things around the 9. So I'll have the absolute value of x minus 2 will be less than 9. You see the center is going to be at x equal 2. The radius will be 9. I already know that r equals 9 because of this. If you know that the center is 2 and the radius is 9, then you could think about being centered at 2. If you went 9 in this direction, then you would end up at 11. If you went 9 in the opposite direction, you would end up at negative 7. But if you don't like that, then take this inequality and rewrite it as negative 9 less than x minus 2 is less than 9, and that add 2 through, and you'll get negative 7 is less than x is less than 11. And so this is close to the answer. Remember, we have to check the endpoints. So endpoints. And we'll start with x equals negative 7. And let me go back to the series that I had. That was x minus 2 to the k over 3 to the 2k. Or actually, I'm going to use this version of it. I like this better. So I'll have, and it doesn't matter where it starts. So I'll x minus 2 over 9 to the k. That will equal, so when I plug in negative 7, I'll get negative 7 minus 2 over 9 to the k. And this isn't going to converge. It's an alternating kind of a sum. So you'll have, I'll put DNC for does not converge. It doesn't equal infinity, but I think what you'll see when you try x equals 11, it'll give a series that's just basically 1 to the k, and that's going to equal infinity. So neither of the endpoints work, so this is our interval of convergence.